This pile of formulas is the trig identities you have to know in high school. Yet it looks like a pile of mess that makes zero sense. And truthfully speaking, I agree with you. Just looking at these formulas basically mean nothing. However, in this video, we will cover everything from the basics of triangles all the way down to these triangle trig identities and make them click forever. Because in reality, they are not hard, and I can summarize them into short points so that you will never forget these formulas. We will use logic to analyze why mathematicians came up with these ideas and how these derivations are done and how to remember them cleanly and clearly. Let's begin. So in this video, we will start by talking about the basics of triangles. For a triangle, of course, there are angles, and there are also edges. Apart from that, we will then move on to calculating areas. Meantime, there are some special lines or segments in the triangle, which we will cover next. Finally, we will analyze the relationship between two different triangles, namely similar triangles, because these are generally what matters the most. And then finally, given all this information, we can then move on to study some trig identities, and then finally attack some problems. And let's dive in immediately. So, to begin with, we will analyze angles. There is not much to be talked about here. It's basically that in a triangle ABC, let's draw it. Suppose we denote this angle's measure as m of a, measure of a. Then we have measure of a plus b plus c is simply equal to 180 degrees, or sometimes we write this as pi as well. So here it's the degree form, and here is the radian form. Essentially, what it's saying is that if we treat an angle as two segments of length 1 centered at point O of the xy coordinate plane, then you can treat an angle of 180 degrees as moving from the positive x-axis to the negative x-axis, and the distance that the segment travels is exactly pi. Let's illustrate this. So the point we're focusing on here moves like this over here, and this length is pi when this length is 1. Well, that's all about angles. And then let's talk about edges as well. So previously, mainly what we have learned about edges is sublight trig and also the Pythagorean theorem, which states in a right triangle, we have a squared plus b squared is equal to c squared. And generally, we use this to calculate length. But have you ever wondered what happens when we change the angle? For instance, here it is not 90 degrees anymore. Can we calculate it? The answer is we can. How? For instance, in the triangle we have drawn here, we can draw a line perpendicular to BC from A. And then that creates two right triangles, so things are going to be easier if we work with trigonometry or the Pythagorean theorem. In this case, let's denote the side length opposite from the angle A as small a, and similarly small b and small c. Then we can represent AH as c times sine b. And also BH is equal to c times cosine of b. Then that means CH is A minus C times cosine of B. In this case, we can apply the Pythagorean theorem to the triangle AHC. That means AH squared plus CH squared is exactly equal to AC squared. In this case, let's just plug these values in. We have C squared times sine B squared plus A squared minus 2AC times cosine of B plus C squared times cosine squared of B is then equal to B squared. In this case, notice something really interesting. We have the term sine squared B plus cosine squared B, which happens to be equal to 1. We will show why this is true when we talk about trig identities, but this is the most basic trig identity, and I think you might have already learned this in middle school as well. In that case, we can simplify the above equation to b squared is equal to a squared plus c squared minus 2 times cosine of b times ac. And this is called the law of cosines. It is essentially saying that if we are given the angle opposite to a side length and the side length that's adjacent to this angle, then we can find the original side length b. And again, drawing from the inspiration of creating this perpendicular line, we can also observe that something interesting. Because to represent AH, there are multiple ways, including B times sine of C. So from this expression, what can we derive here? We can reverse cross multiply this thing, then it becomes C divided by sine of C is equal to B divided by sine of B. Similarly, we can obtain the exact same result for A. So overall, A divided by sine of A is equal to B divided by sine of B, and is equal to C divided by sine of C. This is the law of sine. Combined, these two methods are the main ways for us to calculate side lengths in triangles, given the angles and sum of the side lengths. Next, let's talk about area. We can draw inspiration from the perpendicular line again, because originally we know the area of ABC, we write it as this, is equal to BC times H. And since we have these representations of H, for instance, we can select this one, then it is actually simply equal to AC times, oh, I forgot the 1/2 here, 1/2 times sine of B. So this is the area formula. Two side lengths in the triangle, and the angle made by these lines can decide the triangle's area, which is given by this formula. So this is the basic area formula. However, perhaps you're wondering, if I do not know any side lengths, can I find the area of the triangle? Of course, yes. Given three side lengths, of course, you can find angle B using the reverse of law of cosine. Or to be specific, we can move this to the left-hand side and move this to the right-hand side. And some simplification gives the result cosine of B is in fact equal to a squared plus c squared minus b squared divided by 2 times ac. So you can reverse the process of finding side lengths to finding angles given side lengths. In that case, since you know the cosine value of b, you can find the sine value of b as well. And after that, you can plug it into the original area formula and find the result. However, let's see if we can derive something cleaner just from this inspiration. Let's try. So let's write S equals the angle of ABC for short. S is, of course, already known. We have this expression, and now essentially we're trying to remove this term so that we can get a cleaner formula. Since we know sine squared of an angle is 1 minus cosine squared of an angle, again, this very useful little trig identity, we need to square it to apply this identity. So we square both sides. We can move the 1/2 over, so it's written like this. And now we plug the cosine value in. The reason that we really want the cosine value is that you can see that the sine value is more closely related to the ratios of lengths, but the cosine value can give inspiration directly on what the lengths are. So in this case, we can plug it in to obtain this. Now, recall that we have written cosine of c is equal to a squared plus b squared minus c squared over 2ab. Then naturally, the square of this is 4a squared b squared under this expression put in parentheses. Because this thing is really huge and we don't really want to expand it, let's just put it like this for now. And then that means the original expression can be written as a squared b squared minus, notice that it actually cancels off, like this term and this term actually cancels off when we multiply it over. So we have this. And now again, let's move the 4 over. So 16x s squared is equal to this. Notice that these two expressions are in fact squares. So we can apply the difference of squares identity. Recall that x squared minus y squared is equal to x plus y multiplied by x minus y. We apply this, then we get, actually we forgot the 4 here. So anyhow, it is still a squared expression. Let's rewrite this again for clarity. And then now we can apply the identity. So it's a squared plus b squared minus c squared plus 2ab multiplied by negative a squared plus b squared minus c squared plus 2ab. And from this, you can actually observe a square formula, so it can again be written as the difference of two squares. So in fact, this expression can be simplified or factorized further to look like this. And then let's deal with this term. First of all, we can move the negative sign outside so that we have to change this sign over here to negative. And then again, we can apply the square identity because we observe that it can be factorized into this. So again, we factorize that. It gives us a minus b minus c multiplied by a minus b plus c. In this case, we can put this negative sign into this expression over here. So it's negative a plus b plus c. So actually, the four terms have some great patterns because the first term is simply that nothing changes here. Like it's all positive. Then C is negative, then B is negative, then A is negative. So that's a really nice formula. And now, of course, we can rewrite this even better according to, so the ultimate form here is actually called the Heron's formula, where it is written as this. The area of triangle ABC is the square root of S times S minus A times S minus B times S minus C, where S is equal to the semi-perimeter, or A plus B plus C divided by 2. You can plug S back and you will see that it is exactly the same thing over here. And arriving at this conclusion really simplifies our calculation, so this is a very useful formula when we're trying to calculate areas. Next, let's also look at some very useful special lines in a triangle. The first of which is the perpendicular line, which we have already seen. Next, let's look at the angle bisector of the triangle. Namely, we can draw a line from A, and essentially, it is going to divide these two angles. And let's say it intersects segment BC at D. Then AD is the answer of BAC. So what is special here? It might require you to try around a bit, but what you notice is that these two angles are the same, this length is the same. So actually, given our area formula, the area of BAD to the area of CAD, the ratio is actually dependent of the length AB and AC. Also, you might notice since that both the triangle ABD and ADC have the same height, or if we draw a perpendicular line from A to BC, both the base BD and CD shares it. So in fact, the area of these two are also equal to the ratio of BD over CD. So again, we arrive at a very useful conclusion. So we derive this using area, which is the pure reason that I first talked about area and then these special lines. And the angle bisector theorem is exactly this statement, which is very useful. And then also we have another special line. This time we take the midpoint, D. Connecting it gives us the median. What is special about the median is not that this one single point has anything special. Of course, it has a lot of things special, but it is generally not what we need to know about. And even if it is required, I think most of you can find those information right from the problem statement yourself. So we don't really need to worry about D being the midpoint because there's way too much to talk about for midpoints that you can just remember. You really do have to understand how midpoints work in problems. We will show an example very soon. However, what is special about the median is that we also have a point called the centroid, which is the intersection of two of the medians. And you can prove this yourself. In fact, the third median also passes through the same centroid. Similarly, of course, we also have other centers of the triangle, which we will go back to in a minute. So in this case, what is special about the centroid is in fact the ratio of these two lengths. And how can you arrive at a conclusion of this type? You can utilize the fact that you're dealing with medians. I hope you have learned before that there is the statement that for two middle points of two segments that have the same angle here, then in this case, for example, DE is parallel to AB and is 1/2 of AB. In this case, you can create a new midpoint, which is very useful for midpoint problems. You can generally try to do something with a midpoint. In this case, you can create a new midpoint here, and then you will notice that by the theorem I just mentioned, these two lines are parallel, and DF is 1/2 of BE. But this is not actually the most important thing. It is the fact that this is equal to this. So EF, suppose it is X, and CF is X, and then here it is 2X. Since it is parallel, so let's say the center here is O, then AO over OD is equal to AE over EF, which is exactly 2. So this is the centroid identity. And as I mentioned, there are other centers of the triangle. And first of all, the orthocenter, which essentially means taking another perpendicular line. And of course, we can take another perpendicular line. Again, it all passes through one same point. You can prove this yourself. But orthocenters, it doesn't really have a lot of information, at least in this phase of learning math. In the next lesson, we'll talk about cyclic quadrilaterals, and you will learn by then that every such quadrilateral, which is made of one vertex, two perpendicular feet, and then the orthocenter is a cyclic quadrilateral. And of course, that gives some information, but we'll talk more about that in the next session. Next, the other two centers are also largely related with triangles. For instance, in this case, the intersection of the angle bisectors is called the incenter because you can draw a circle with a certain radius here that is tangent to each side of the triangle. Why? Because if we take the perpendicular line to each edge, of course, I can't really draw that accurately on this pad. So if we take this length, we have the same angle and the same length here. So in fact, this perpendicular segment and this segment has the same length. So if we take a perpendicular line to any edge of the triangle, we have the same distance. So that means it is essentially tangent to all three sides of the triangle. And there's also the circumcenter, which is just the circle that is located outside of the triangle, which passes through all 3 points ABC, which is the intersection of the perpendicular bisector of all three lengths. And that's really easy to understand because it's essentially saying that the distance from the circumcenter to all 3 points are the same. So that is the four centers of the triangle. But I think apart from the angle bisector theorem and also the centroid identity, apart from these two, the rest is just understanding the characteristics of these special lines in a triangle. And that's all. So finally, we should probably talk about similar triangles, but here I am assuming that you have already learned similar triangles in middle school. So similar triangles are a really important tool in geometry, and basically every hard problem is related to similar triangles. So essentially what you really require is actually a better usage of them rather than gaining more information about these similar triangles. So we won't talk too much about it right here, and I think it's time for us to embrace trig identities. So the first two are very basic. Essentially, tangent of x is equal to sine of x over cosine of x is a really definition-wise formula. And this is really easy to understand as well, because on the unit circle, as we mentioned in the lesson, complex numbers, any point on the unit circle has the coordinates cosine of theta and sine of theta. So naturally, since this length is 1, then cosine squared of theta plus sine squared of theta is simply 1. Next, things get a bit crazy. For instance, have you ever wondered, suppose this is alpha, this is beta, then what is the coordinate of this point? This is essentially asking us to find cosine of alpha plus beta, comma sine of alpha plus beta. And the tricky thing here, of course, is that you cannot simply say cosine alpha plus beta is equal to cosine alpha plus cosine beta. That is absolutely wrong. So what can we do here? There are multiple ways to prove it. So before we mentioned that this is easily provable with the De Moivre's theorem and also complex numbers. But also we want to prove this geometrically. So in this lesson, I'm going to show it in a very geometrical way where alpha and beta is between 0 and 90 degrees, because that's where angles are easy to understand geometrically. Of course, there is another method, which is we start not from sine of x plus y, but rather sine of x minus y, because that means essentially we are taking an angle out and we're considering this part of the radian, which is also an interesting way to deal with it. So I won't go too much into the details. You can try it yourself, proving sine x minus y first, and then plugging in y where y is actually negative y. So essentially, you can say where you just plug in x is equal to alpha, y is equal to negative beta, then if we apply this formula, we get sine alpha plus beta. So essentially, x plus y and x minus y can be transformed from one to the other. In this case, let's use our triangle way of proving it. Here we have alpha and beta. So assume this length is 1. Then essentially, sine x plus y is this length down here. This is sine x plus y. And over here, this is cosine x plus y. And if we have cosine x plus y and sine x plus y, we can find tangent x plus y. So the way to go here is you begin with realizing you don't really have a way to cleanly represent these angles. So you don't really have a clean way of representing these lengths. Then what do? You try some auxiliary lines. And I think the best auxiliary line here is we extend it and take a perpendicular line. And the reason of which is that we actually managed to pass down the information of alpha over here to this point. So that means this length is simply sine beta. With that, we can continue to represent this length over here as sine of beta over cosine of alpha. If you can't really follow me here clearly, you can watch this part of the video again, and then you can try to follow the logic, because sometimes for those that has just learned about trigonometry, it is difficult to track why just plugging in, like multiplying or dividing by certain values makes sense. So you can rewatch it. So this length is sine beta over cosine alpha. And also that means we can find this length. So originally, this length should have been sine of beta times tangent of alpha. But here, since we're first focusing on the sine identity, and we don't really want a tangent here, then let's write tangent as sine alpha over cosine alpha. Also, remember this length is cosine of beta, so the long segment here can be written as beta minus sine beta times sine alpha over cosine alpha. As a last step, let's denote this as x for short, and this length over here is x times sine of alpha. Then essentially, we have sine x plus y is equal to x times sine alpha plus sine beta over cosine alpha. And then let's plug in the values. That gives us cosine of beta times sine of alpha minus sine of beta times sine of alpha squared over cosine of alpha plus sine of beta over cosine of alpha. And now since these terms have a cosine of alpha, let's multiply this term by cosine of alpha as well. So we have cosine of alpha multiplied by sine of alpha minus sine of beta times sine squared of alpha plus sine beta. Now, this part is in fact simply equal to sine of beta times cosine squared of alpha, right? Because cosine squared of alpha is equal to 1 minus sine squared of alpha. And then we can cancel off the cosine alpha here to gain that this length is simply cosine beta times sine alpha plus sine beta times cosine alpha. Don't get distracted by the problem down here. We are focusing on the angle addition identity. And then similarly, we can also find this length, because this is simply x times cosine of alpha. So that means cosine of x plus y is equal to cosine beta times cosine alpha, and luckily these two terms cancel off, which is minus sine beta times sine alpha. So we have these two equations. And then given that, we can find tangent x plus y. And the way to go here, let me just clean this part up. Boom, is tangent x plus y is equal to sine of x plus y over cosine of x plus y, which we already have is sine of x cosine of y plus cosine of x sine of y over cosine of x cosine of y minus sine of x sine of y. And then here, we can divide the up and down parts of the equation by cosine x cosine y to obtain tangent values, because if we divide by this value, we simply get tangent of x on this term plus tangent of y on this term over 1 minus tangent x times tangent y on this term. And we're done. We gain the third identity. And from here, given these identities, we can find very interesting things. For example, let's say you plug in x equals y. Then we have sine 2 theta relative to theta. And then we also have cosine 2 theta relative to theta. And a note here that cosine 2 theta is actually really nice to write out, because it is equal to cosine theta squared minus sine theta squared. But this is actually equal to 2 cosine theta squared minus 1, or 1 minus 2 sine theta squared, which is useful information. And then reversing, of course, you can have tangent 2 theta as well. And then you can reverse this, because given 2 theta, you can also find theta by listing out a quadratic formula. So you can actually represent half angles as well. So from these three, we have the double angle identities and the half angle identities, which I didn't even list here, but I can write like another half page. But it is actually really easy to understand, and the more you use them, the better you will remember them. So you can try to list out sine 2 theta, sine half of theta, cosine 2 theta, cosine half of theta, and also for tangent as well, and try to use them without looking at your formulas when you do problems. Next, it's this bunch of crazy looking stuff, which is called the product to sum identities. And it is actually easy to understand because when you counter equations related with the product of trig values, then you can expand it to sums to potentially find something interesting. And really, it's easy to understand how we came up with these formulas. Namely, you first calculate this half, and you realize you simplify it down to the original version. But why did we came up with this idea? Actually, it's not that hard to understand. Let's take cosine, for example. We know cosine x plus y is equal to cosine x cosine y minus sine x sine y. We also have cosine x minus y, which is equal to cosine x cosine y plus sine x sine y. In this case, if we add up the two parts, we're left with 2 cosine x cosine y, or we can also subtract the first one from the second one, which we get 2 sine x sine y. And similarly, you can do the same thing for this. So it is actually using the fact that when we flip the signs, only part of the equation get negated. So you can derive some interesting formulas from this inspiration. Next, we also have the sum to product identities, which came from similar inspiration. You first find the second half, then you obtain the first half. And in reality, it is actually just the reverse version, because if you study these two equations, then you can let this be alpha, this be beta. Then in this case, if you move the 2 over here, then actually it is just the same formula, except you're writing it in a different way. So that is essentially how the sum to product formulas work. And you might have noticed that I am really skipping a lot in these formulas because, first of all, product to sum and sum to product formulas are rarely seen. Secondly, it is easy to derive yourself and difficult to remember. So it's better that you remember how we came up with these ideas and utilize them and derive the formulas yourself when you're solving problems. Before we try our skills on some problems, I should mention, don't forget to draw the unit circle when you're tackling special angles. For example, if I ask what is sine alpha plus 90 degrees, you can draw the unit circle, for instance, let this be alpha. Then if we plus 90 degrees, you would realize that these two triangles are just congruent. So sine alpha plus 90 degrees is actually the negative of cosine alpha, because this length is equal to this length. And that's the power of unit circles. These I didn't really put as formulas here because there's way too many cases, but you can just draw the unit circle and understand it yourself. Now, problems. The first one, an easy problem to start with. Take a moment and look at it. So this problem inspires the Heron's formula. For the first triangle, we have an area of 12 and semi-perimeter of 9. And of course, since there is a semi-perimeter of 9, we also have A is equal to 9 minus 1 half of B. Now apply the Heron formula to the second triangle. We arrive at this equation. You can derive it yourself. And since we already know that B equals 8 is a solution, so we can factorize B minus 8 out of this thing. So in fact, we arrive at the result. This equation is nothing different from this. And let's just solve for this. We get B is equal to 1 plus or minus square root of 33 over 7. Of course, we can't take the minus sign, so it's only the plus sign, which is approximately equal to 3.37 if you have a calculator. Of course, you can just move out the 7 and then analyze the upper part if you don't have a calculator. Next, a problem related with arithmetic progression. The angles are an arithmetic progression. What can you think of here? In the next, we also know the side lengths are 4, 5, and x. So we're to find the possible values for x. Well, first of all, we can write the initial angle as alpha and the common difference as beta. So we have this. But notice, when we add all of these up, we have it is equal to 180 degrees. So alpha plus beta must be 60 degrees. That is useful information. Now we can plug in the law of cosine to possible middle sides. Because 60 degrees is the middle length, then that means we're looking for the middle length, 60 degrees. That means alpha plus beta is 60 degrees. Now, Using law of sine, we can derive that if an angle is big, suppose A is the biggest angle, then small a must be the largest length. So the 60 degrees angle here is corresponding to the length that is in the middle. Of course, 4 cannot be the middle length, so the middle length can either be 5 or x. We can plug in law of cosines to solve. We get two possible equations, or of course x squared as well. And solving these give x is equal to 2 plus square root of 13 or square root of 21. So the sum is simply adding up both because because both solutions satisfy that this length is exactly the middle length. In this case, this one is larger. In this case, this one is less than 5. Next example, we're looking at angle bisectors. I think I forgot to put the source of the problem, but this is an AMC12 problem. Let's draw the diagram. We are supposed to find AF over FD. This is not the centroid, so AF over FD is not 2. Then what can we do here? First of all, we can apply the angle bisector to this bisector. Then we have AE over CE is equal to AB over BC, which is equal to 6 over 7. This is just a rearranged version of the angle bisectors theorem. And then since AC is 8, so CE is 8 minus AE. That means this. Solving this gives AE is equal to 48 over 13. Similarly, we can apply this to AD to find that BD is 3 and CD is 4. And remember, the angle bisector not only bisected this triangle, ABC, it also bisected ABD. Well, is this information useful? AE is equal to this value? We're not sure, but let's apply the same thing to the other angle bisector as well. That means BD is 3 and CD is 4. And remember, BE is not only the angle bisector of ABC, it is also the angle bisector of ABD. So the same theorem applies to AF over FD is equal to AB over BD is exactly equal to 2. So I actually trolled you when I'm saying AF over FD is not 2. But of course, this is not the centroid. It just happened that AF is equal to 2FD. Next up, an interesting problem. And I recall when I'm doing this problem for the first time, I just got stuck because it didn't really make sense to me. Just like, what are we supposed to do given such a problem? But in the end, it just turned out we're just trying our luck, and trying a little bit gives the result, so don't really worry. There are two solutions to this problem, and the first is just letting tangent alpha equals 3 or over 4, tangent beta equals 7 over 24. In this case, you notice tangent alpha plus beta is actually equal to 4 over 3 or 1 over tangent alpha. Then that means alpha plus beta is this. Use the unit circle to understand why I came to this conclusion. And this is actually just the algebraic version of putting a triangle side by side like this. 18, 24, 30, and you also have the length 4 over here. And since both lengths are 25, so this angle is equal to this angle, which can give us the same result, which is really interesting. I think this problem is well designed, and it is one of those problems that doesn't seem obvious, but it requires a little bit of luck. Let's keep on moving. So this time, we are actually working with the centroid. And we know that this is a equilateral triangle. What information can we gain here? So this graph is a bad graph, and as we mentioned literally in the first video, don't worry when you draw a bad graph. You can build on the information from this graph to draw a better one. And this time, it looks a lot more reasonable. In this case, we are to find cosine of c. And now remember, we don't really care about the side lengths. We only care about the angle. So without loss of generality, we can set values. Like, no matter what value we set here, it's going to be the same result. So we just let AG equals GE equals AE equals to 2. And then since it is the centroid, we have these lengths. And of course, CE is 2 because E is the midpoint of AC. From there, since this is 60 degrees, we can apply the law of cosine to triangle ADC to find that CD is square root of 13. Then BD is also square root of 13. Then you can either apply the law of sine to ADC or the reverse law of cosine to find cosine of C because all side lengths are known. The answer you can try to solve yourself is 5 over 2 square root of 13 or 5 times square root of 13 over 26 if you like. Now, let's look at some more difficult problems. The first one related to a minimum possible value. And the reason that these problems are difficult is because generally the better way to attack them is actually through auxiliary lines, which is not easy to discover. But let's just take a moment to look at this problem. We have a point D on AB and a point E on AC. And then connecting the lengths it requires gives us this, where to find the minimum possible value. And this thing looks really impossible just to bash out through trig. So I think the way to go here is to convert the side length. And you can take a look at this yourself. And if this is the first time you're tackling something like this, it's going to be challenging. But let me just show you, okay? Show you the logic I go by. First of all, we know that the 40-degree constraint is really not that useful, and most likely the only way to use it is multiply it by 3 and get 120 degrees. And also, let's see if we can construct something that is equal to DE, which is done by reflecting the ray AC by AB and then taking exactly the same point and reflect point C over. Let's say this is M. So MD is equal to CD. Similarly, do the same thing on the other side. You reflect the point B, then this is BE. NE is equal to BE. So the length we are concerned with is just this squiggly thing. And the shortest possible version, of course, is the non-squiggly version, exactly equal to MN. Applying the law of cosines, find the length of MN easily, which is 14, and we're done, which is an interesting way to solve the problem. So here we're just going by logic and determining what we need for an auxiliary line to convert the problem into something simpler. You will learn to do an auxiliary line yourself in another problem. So last problem of the lecture, this one, another auxiliary line problem. So take a moment and look at the problem statement. And actually, I can tell you this thing can be generalized. And we are to find the angle between MN and AP. For this problem, there is a way to solve using trig bash because it is relatively easier compared to the last problem. But if you're interested, just check it out in the materials in the description. But in this case, we're going to analyze how to come to the conclusion using auxiliary lines. When you notice there's one midpoint, you really want to construct that identity with two midpoints in a triangle, right? Using something like similar triangles, you can say. But this is just a special model, 1, 2. What to do here? Then you can try to construct exactly this triangle, which can be done by extending this to double its length. And then when we connect this, let's say this point is Q, let's just say this point is Q, then we know GQ is parallel to NM, and also GQ is equal to 2MN, which isn't really important in this problem. Now, this transports this angle over here to this angle. And what's even more interesting is when you connect AQ, you notice that these triangles are congruent. So in fact, since this is 56 degrees and this is 36 degrees, we can just move it over. This is 56 degrees, so over here it is 36 degrees. So angle PA is 36 degrees. And remember, AG is equal to AQ. So given the combined angle GAQ is equal to 92 degrees, we can find angle QGA, which is 44 degrees. Then that means the combination, then that gives us the answer because we're trying to find this angle. Then that is 180 degrees minus 4 degrees minus 56 degrees, which is equal to 1 degrees, and we are done. So this is actually a very classic model, like just extending the midpoint to double its length and then trying to use it like in another midpoint and utilizing the fact that there is a congruent triangle, a very common auxiliary line. So another interesting auxiliary line problem. And then of course you can try to solve this using trig yourself and check down below. So we're done for today, and down below is some extra problems for you to practice. First of all, review the proofs, essentially those trigonometric identities, and then we have the practice problems. So the first one is a really simple problem that is just practicing your basic skills. The next is another relatively easy problem that is just concrete triangles. You just need to utilize what we learned today. So this one is a lot more interesting, and try to use all the information in the problem. Be sure to use them all, otherwise you can't solve it. This is one of the hardest problems in triangles, and you can just get a feeling of what a difficult non-analytic geometry problem looks like. This problem can also be simplified if you're willing to use some auxiliary lines, but I think without auxiliary lines you can do okay as well. But auxiliary lines sometimes can simplify the problem-solving process. And of course, apart from that, we will have non-standard problems. This requires auxiliary lines, and of course you can use brute force as well and try it out, but it's going to be a lot more difficult. The last one is actually something slightly distant from the problems we practice today. This is just a really offbeat problem, so you can think about it yourself and see if you can solve it independently. It's a fun problem to think about and practices your problem-solving ability a lot. And that's all for today. I will see you in the next video talking about cyclic quadrilaterals. Bye.